continue. So this part will have a single lecture that will be given by Robert Piltz. So without whatever you will tell us.
Yes, thank you, and thanks to the organizers for giving me this opportunity to present our work. Yes, so measurements of three-body reactions in a cryogenic ion trap. This first slide, I probably don't really need it because we've heard about this a bunch. You can look at three-body reactions sort of in a direct recombination rate where they all come together sort of at once, or also this very, very common way of looking at it, this two-step recombination with in the intermediate state where you have sort of rates of formation and dissociation and stabilization, and from that you can calculate the three-body rate, right? And this is sort of my level of understanding of this all. This rate then also partly depends on the energy partitioning, right? So if your different reactants have more degrees of freedom, this could play a role. And in general, this will result in a temperature dependence of T to the minus n, right? And what is n? Well, it depends on who you ask. There's lots of history on this, many decades of calculations. I don't want to go into these where they come from. I don't really understand it. But the point is, we need that the theory is difficult, and what we need is experimental measurements to get benchmarking to help this along to really try to understand where all this is coming from. And so I am claiming that the cryogenic multipole RF traps are really a good instrument to do this. Pavel already talked about this a little bit. This was sort of designed to do ion neutral reactions. And first of all, it's a very versatile cooling method, right? If you want a new ion, you don't have to buy a bunch of new lasers, right? Just in this talk, I'll be talking about chlorine minus, C2 minus, and argon plus. It's relatively easy to switch. We have a range of temperatures. Of course, we don't get into the ultra cold, but we can go down to 8 Kelvin, up to 300 Kelvin. Our densities of neutrals can be quite high, right? I mean, we have this sort of box that we fill with neutral gas, and we can increase the temperatures, the densities. And for us, we go to really high densities of 10 to the 15 per cubic centimeter. And I really appreciate yesterday Leah's talk. She was saying that you managed to go to really low densities of 10 to the 15 to 10 to the 17, right? So our really high densities and her really low densities are just about touching, which is nice for different methods. And this is also, pressures of up to 0.01 millibar inside our trap chamber. So these are quite high, right? If you're used to ion trapping. And as René pointed out as well, these traps are generally very deep, right? So you have very high lifetimes. Of course, we don't have months of lifetimes. Yes. Is that better? It's the recording. Ah, okay. I just kind of figured I'm pretty loud, so I don't need it, but this is the wrong one. Yes? Okay. Okay. Where was I? So we have, yes, we can't trap our ions for months, but we do have trap lifetimes in the scale of hours, which is plenty long for our experiments. Of course, all these numbers look really good. I do have to say that we rarely can get all of these parameters at the same time, right? So you kind of have to pick and choose which ones you want. We used to have this 22-pole trap, which is very similar to the one that Pavel showed. We have, in the meantime, switched to our newest sort of wire trap with 16 poles, but the principle is the same. And these kind of traps, like I said, are good for measuring low reaction rates, right? With high densities and long times. So you can really three-body reactions are often very low. And one example of a measurement like this is a bimolecular rate that we measured recently. This is a proton tunneling, where a proton tunnels from H2 to D-, and this is an extremely slow rate. It has a reaction probability per collision of about 10 to the minus 11, right? And then we were successfully able to measure this, and if you're more interested in that, we have a poster on that as well. But anyway, so these seems like it might be good for three-body reactions. How does this work in our setup as a whole? Well, we create our ions in a plasma source, so very, very rough, right? We just have a pulse of gas and make all sorts of ions. And then we accelerate down this tube and just do mass separation by time of flight. It's relatively simple. Then we bend our ions into this trap where we have our buffer gas. This buffer gas is, this thermalizes with the trap walls. This trap is mounted on a helium cryostat. And so this buffer gas then cools the ions through collisions. And if we want to know how many ions we have in the trap, we then just extract again, bend it around once, reflect off here and onto our detector. So once again, we have time of flight mass separation. And so, of course, as always, there are experimental difficulties and problems. But in principle, the experiment is quite simple. We create and trap the ions with buffer gas, and this buffer gas can also double as the reactant gas. And then we simply wait, right? And then after that, some waiting time, we extract and just measure what masses we have. Again, kind of similar to what Pavel showed. Okay, so with this method, I'd like to talk about three different three-body reactions that we've been working on or are working on. In one sense, an atomic ion with two dimers, so chlorine minus with H2, then a molecular ion with two dimers, C2 minus with H2, and then at the end, atomic ions plus atoms, argon plus argon. So I'll start with chlorine minus. Here we trapped it in, like I said, very, very high densities, up to 10 to the 15 per cubic centimeters. And this is sort of the time of flight trace that you get out. So after 0 seconds of trapping, all you have is this chlorine minus peak. And after, in this case, 45 seconds of trapping, the chlorine minus is decreased. And you see chlorine H2 appear, but also some clusters. And there are also actually higher clusters that we saw forming as well. Now this we do for long interaction times. You see the x-axis here. This is 500 seconds. We even have, some of these are much longer. So sometimes, a single shot will maybe be 20 minutes. So you can, load your ions and go have a coffee, right? And it's good long times, but also the same problem that you mentioned. If we want to have lots of data, this can really take a long time. But it's quite sensitive. What you see here, though, already is that you see at some temperatures this is leveling off, right? That means that this chlorine minus, this parent ion, is getting repopulated via some back reaction, and it's reaching some equilibrium. So how do we fit this then? We make a simple two-component model. I mean, we have lots of clusters, but we say there's only two things. There's this parent ion, this chlorine, which reacts away with some forward reaction, and then we have some reservoir of all clusters that gets formed, and from that we can back react, right? And so it's just this sort of two-component system. We fit these points and then just look at our forward reaction rate versus H2 density. And then fitting a polynomial, we see this is proportional to, just has an n-squared dependence with a linear dependence being consistent with 0. So we say, okay, this is really a three-body reaction. We call this then K3 and repeat this for different temperatures, which is plotted here. So this is the three-body rate coefficient versus temperature. And this here fits to T to the minus 1 quite well. We ignore this lowest point here, and this is also as mentioned by Renee, that these RF traps, well, you do have micromotion, and micromotion with collisions cause heating, and of course we have lots of collisions. And so that sort of gives a lower temperature limit to how low we can really get, because you constantly have this heating happening at the same time. And so this sort of also told us that this trap, this was the first time we used our new wire trap, told us that we can cool down to 14, but below that the ions don't really reach lower temperatures. So we basically just ignore this point and say we have these points that fit nicely to this T to the minus 1.
So how do you measure the temperature?
Well, in this case, we didn't separately measure the temperature. In this case, we are just saying that the fact that it follows the trend shows that it's still cooling. We have a different experiment I'll come to later with C2 minus, where we did use spectroscopy to do a temperature measurement. But here, yeah, the main point is that the trend keeps going up. So it's not a very strong temperature measurement, I agree. So do we have theory for this? Well, chlorine minus plus H2, that's too many bodies, right, for a full quantum calculation. So what do we have that's close? Well, there are these classical approaches, to doing hyperspherical coordinates. We've heard some of this by Jesus and Chris, and this shows sort of a temperature dependence of T to the minus 3/4. Now, of course, this is for an ion atom-atom system, and that's not what this is, but that didn't stop Jesus from putting this fit on onto our data, right? If all you have is a hammer. I'm just kidding. It is, it does actually not fit so badly, and if you were even to ignore this point here, then it would be a fantastic fit. But it's dangerous ignoring points. But so also this had to be divided by a factor of 3 to get down to this level. But it is compelling, and we are actually interested in doing, say, more in the future on this. We have now a para-hydrogen generator, so we want to do specifically with para-hydrogen. And given this, maybe we should, when we revisit, we'll also do a more careful, do a more precise, take more points and really, lock down what the temperature dependence is really. So the story is not finished here, but it looks, yeah, that's. So this is the forward reaction, the three-body reaction. I also want to, on sort of on the side, mention this back reaction, which actually surprises us that it even happened, right? This thing that's repopulating the chlorine ion. Because this back reaction, we expected that it wouldn't happen at all because we should have a binding energy about 52 millielectron volts. So at these temperatures, that should essentially stay together. And when we plot this back reaction versus density, we see that it has a very clear n-cubed dependence, with the linear and n-squared dependence being consistent with 0. Big question marks, but we say, okay, so if it has an n-squared, we call it k3, so we had n-cubed, we called it k4, right? Who knows? And if we plot this k4 versus temperature, it fits very nicely with this onto a Boltzmann fit with a binding energy of 6 millielectron volts. So maybe there's some, and here we're ignoring, or we didn't include this highest point in the fit because here the energies are, or the temperatures are high enough where you can expect some single collision dissociation. But yeah, so there may be some sort of process here that requires multiple collisions that deposits energy into the system. We're not sure what mechanism that could be. So if you like puzzles and want to think about this, be our guest.
So you're talking about the dissociation after it's formed?
That's right, the dissociation of these clusters, the chlorine H2 clusters or chlorine H22, H23, et cetera.
You had this chlorine minus H2 with two H2s, which you might expect to have a K4. Have you studied its density dependence?
Not that specifically. This is still just the K back, which is the whole assembly. All the clusters sort of in one,
well, that
right?
Includes all of them.
That includes
the trimer.
Yeah. So this is this model where we just say this K back is the sum of these all the clusters of every size. So this is just fitted a K forward and a K backward, and this K backward.
It looks like on that graph on the upper left there that you could see a very clear separation of the two peaks with one H2 or two H2s.
Yes, yes. So we could look into that. We didn't specifically. Okay, so this was the story with chlorine and H2. Now I'll talk about C2 minus, a molecular ion. C2 minus is in itself already interesting. It's one of the best characterized molecular anions. It's proposed to exist in the interstellar medium because there's a lot of C2 around. And it actually has 3 electronic bound states, which is kind of rare for an anion. And because some of these are nice wavelengths, it's a candidate for laser cooling. So we're actually looking into that ourselves. We've done some spectroscopy and also some measurements of quenching for the V equals 1 to the V equals 0 state with H2. And as part of these experiments, we also measured 3-body rate constants. And by doing this spectroscopy, we also measured the temperatures of the C2 minus ions. So what's also interesting about this reaction is that it's actually a bond-breaking reaction. The product is not just a cluster of C2H2, but you have C2H minus left over and a little H either leaving. Well, you can, in principle, do this with a 3-body reaction or a 2-body reaction. And so this density dependence is important, right? And so when we take these loss rates, again, we see a very clear n-squared dependence with the linear component consistent with 0. Except at the very lowest temperature, we may have some signal of this, but nothing concrete. So it really also looks like here, at all the temperatures that we look at, it's mainly a 3-body reaction. So again, just like before, we do this for different temperatures and plot the 3-body rate constant versus temperature, right? And once again, here we leave out this lowest points for the same reason. But here it's not so clear. I'll get back to that later. Here the fit is a t to the minus 0.8 with the error bar actually being consistent with 3/4. And here we add the line because it didn't bother us before. We can do it again. This is an ion atom. Now we have even more degrees of freedom, but it's what we have for now. So the temperature dependence looks to be quite consistent. The amplitude is only about a factor of 2 off, so it's actually not that bad, and maybe that tells us about how important these extra degrees of freedom are in this system. However, we were not just happy to do this. We said maybe we can do some more theoretical modeling and perform statistical variational transition state theory calculations. And when I say that we performed these, I definitely want to say that I had no part in this whatsoever. This is our theory collaborators, and I will try to talk you through this a little bit without making a fool of myself. So the concept here was they did ab initio calculations on the potential energy surface, looking at the minimum energy path to the reactive state. And this minimum energy path is plotted here along the reaction coordinates. So this is the distance between the carbon and the H ion and atoms that will then be bound together. And so you have this little dip here, a barrier, and then the final reaction state. And so first of all, this was also done with the 2 bodies. So here, in this case, this is the 3 bodies. This was also done with just 2. And it was seen that the barrier is much higher, which already kind of explains that the 3-body rate would be the preferred way to do it. And it also showed that this minimum energy path is a collinear approach and not at different angles. Okay, so you have, so this barrier is relatively high, so the reaction then would recur via tunneling through this barrier. And what you also have is that, out here, this is still symmetric, right? So this little dip right here is on both sides, and you have this extra the spectator hydrogen can also gain a little bit of energy by falling into this little well, right? And the question actually is this might influence or be part of the reaction. So let me explain a little more. If you take this minimum energy path and with the tunneling calculate the expected rate coefficients, you have some simple versions. If you just really do it simple and do a completely rigid structure, which is completely unrealistic, and nothing else going on, you get this black line down here, which is very low rates. If you make it not rigid but include vibrational rotational coupling of the C2H2, which will then eventually react, you get much higher rates, but still about a couple order of magnitudes below the region, sort of what we were measuring. But if you say, okay, this spectator H2, which gains energy by falling into this little well, if that energy is transferred to the other side, or to the system, if you take the 100% of that energy to transfer it, then you expect, then you get this red curve, which is actually significantly above our reaction rates. So then, you can simply say, well, maybe not 100% of the energy is transferred, but some fraction. What fraction would that have to be? Well, the fraction depends on the temperature. So these are our data points, and you can just plot these lines for different fractions of energy that are added, and say, and just match up, which for each point you can just pick the fraction that matches best, and plot that here. So here now you have the fraction of energy transfer that would fit our data versus temperature. And this actually fits very nicely on this Bose-Einstein type fit with omega over kT. Now, the blue line is the omega is the energy of this vibrational bending mode of this full object, which is quite reasonable. And if we say, okay, well let's keep omega as a free parameter, then you get the yellow line, which fits nicely, and this and the actual value is not that different from this bending mode fit. So what this looks like is that the spectator molecule is gaining some energy and is transferring part of that via this bending mode to the system to allow it to react. So what's also kind of interesting here is this lowest point here actually fits on this line very well, right? This is the one that we said we'll ignore because it doesn't fit on the red line. And here, if it was up on the red line, this would be significantly higher, right? So it wouldn't fit here. So what does that tell us about our temperature? Going back to our temperature measurements that we did with spectroscopy, what we found is that the translational temperature is quite high. So the RF heating definitely heats the things and makes them fly around faster. But the rotational temperature, the internal temperature, did follow the buffer gas down to much colder, right? And so that suggests that here it's the rotational temperature which is really the important part, and why it lies on this curve. So what this means in terms of the T to the minus n is maybe a little bit more difficult, because now you have two temperatures that you have to think about. I'll leave that problem to other people. Okay, so this was the C2 minus H2. And for the last part, I'll talk about the atomic ion with two atoms, argon plus argon. I call this the laughing pirate reaction. Thank you. So this is part of a joint program called the Joint Experimental and Theoretical Determination of Ion-Neutral Three-Body Association Rates, with a very sexy acronym, JETDIN 3-bar. Right? This is a 4-year program that we have with theorists from Bordeaux, including Thierry, Slava in Florida and us in Innsbruck. And the idea of this whole program is that we want to build up understanding of three-body reactions, right? So we want to start with really simple ones. We have some ion with rare gas, and then ion with para H2, and then with normal H2. And this ion should start out with a rare gas, and then we go to closed shell and diatomic and polyatomic, and basically start out with the simplest theory, and then, consistently or in steps make it more complicated, where you have to make more and more assumptions, and these assumptions can be calibrated to the simpler ones. That's the idea. So we start out with, of course, the very simplest version, which is the atomic ion and atoms. Now, this is not the first time that this has been looked at. Here's I grabbed from this paper from 1998, where they actually also put together different measurements. And here that this line sort of fits on a t to the minus 1. I make no comments about that. I don't know. Yeah, but we want to repeat this, first of all, to sort of prove to ourselves that we can do it, and also because we can maybe get some very high accuracy measurements in this regime. And why do I say that? Is because all of these sort of lower measurements, lower temperature points, are taken with gas expanding into vacuum, right? So the Keizu, or the supersonic flow, you have some gas, and it does supersonic expansion, and then you do some ionization at the beginning, and then these ions, they react at high densities, and as they fly out, they react for longer times, and it's probed at different points, or to see what ions are left. And of course, I don't want to say that these are bad measurements, but as this is expanding, you're also changing the density, you're changing the temperature. This is all non-trivial, right? And so our method also has its own problems, but at least it's a completely different method for independent verification of these measurements. And at least the density and the temperature at higher densities and temperatures for us is maybe it's not trivial, but it's pretty straightforward. I mean, we measure a pressure, and we measure the temperature of our copper block, right? So there's not that much that we can do wrong in that sense. Okay, so of course, this doesn't mean it's easy. We also have problematic reactions. So this is, as an example, going back to, this was what we saw in chlorine. We saw a nice increase of chlorine H2 and maybe a cluster. Here's our argon peak. It goes down, sure. We have argon 2+ that goes up. And then we have things like O2+, we have N2+ that goes up and down. We have N4+ that increases, N2+ argon a little bit over here. Because argon is very reactive, and there are these other things in our background, just in the vacuum background, or in our buffer gas that it likes to react with. And so when our chemical model for this thing was quite simple, here we have to consider all the things that are maybe going on, one thing moving to the other. We're not sure yet exactly what's going on. This is really quite preliminary results. This is data that we took 2 weeks ago, and fits that we did last week. So we're still working on it. But here's just two examples. At 80 Kelvin, 2 different pressures, doing a simultaneous fit to all these peaks with the chemical model that I just showed. And you can see, okay, there's still something missing. We're not really quite getting this increase well, or this decrease. But this higher pressure, we do seem to be getting it a little bit better. And from these fits, we can extract a 3-body rate. And of course, because the fits aren't perfect, this is very, very preliminary, but this 3-body rate also seems to have let's say, this rate seems to have a very clear n-squared dependence, meaning it is a 3-body rate. We do have a little bit of linear in here, but that's probably due to these issues that we still have. And because there's still issues, I also don't want to actually say that, give a number, but I do want to say that it falls into the right ballpark, and we've taken measurements in this temperature range from about 67 Kelvin to 120 Kelvin. So once we get this figured out, we're optimistic or hopeful that we can have some really nice nicely accurate temperature-dependent rates of this, three-body rates of this reaction. Yes, so with this, I'm already at the end of my talk. So I've told you about measurements of an atomic ion with two dimers. These are all pretty low rates. This one is in the region of 5 times 10 to the minus 31 centimeter to the 6 per second, where we have a T to the minus 1 fall off and a strange back reaction. We measured C2 minus plus H2, which is a bond-breaking reaction, also a little different than normal, where we get this T to the minus 0.8, maybe, but we did modeling that seems to at least model the results very nicely. And we are still working on the argon plus 2 argons in the region of 10 to the minus 30, but there are still some chemical issues that we have to figure out. So with that, I'd like to thank the co-workers that are working on this, our theory collaborators, and all of you for listening.
Thank you very much. Very nice talk. And in fact, I had the pleasure of seeing your go to Innsbruck and see the ion trap myself. It was a fantastic tour. I have a kind of amateur question here. So to resolve these temperature dependence issue, one would think you can simply increase the range of temperature you measure, right? Now I understand going cold is difficult, right? Going colder is difficult. But what's really the difficulty when to do something at higher temperature?
Yeah, I mean, I kind of knew this question was coming, right? Because the plots kind of end around 28 or 30, and why not just keep going? Yeah, exactly. When I said we have a range from 8 Kelvin to 300 Kelvin, and I said we have long lifetimes, right? And I said we don't have this all at the same time. It's sort of also related to this here, right? The colder you go, the more things freeze out and the more pure our vacuum is, or our gas is, which is fantastic. So at these low temperatures, we don't have other dirt in there. We call it dirt. Once you reach higher temperatures, more and more other gases go in, and you start to have other reactions. Our lifetimes go down, and it's also, our densities also increase with temperatures. So we have to reach the same density, we have to let in more gas at higher temperatures, and this all, adds together to make it not such nice points anymore. I mean, you can also see here that the error bars are larger on this point for a reason, right? Because we're starting to hit that limit.
Okay. So the limit is quite short. It's 28.
It really depends. It really depends on what we're looking at, right? Like here, we're working already at 80 Kelvin, and we're going to 120, and we have these other reactions. Here, we can revisit it. Maybe we'll try harder next time to see if we can stretch that out a little further. But I wouldn't call this a hard limit. It's just when we stopped then, because it was already difficult, and yeah.
Another maybe simple question. How do you actually do the temperature control?
So it's pretty basic. These cryostats, they don't, they have an on and off, right? And so when you turn it on, it does maximum cooling. And so then we also have just heaters that these rods that are in our copper block for our trap that we just put current through, and then it heats, and then this thing's heating, this thing's cooling, and it reaches some equilibrium. So we just change the amount of current that goes through.
Okay. So we just wait for the heat to dissipate and reach kind of equilibrium.
Yeah, basically. I mean, as we're cool, we usually don't. It's usually not a good idea to cool all the way down and then heat up, because then you're starting to get rid of all the things that have been frozen on, right? So as we're cooling down, then at the right moment, we turn on the heaters, and then it just kind of stabilizes in that one temperature.
Thank you.
Yep.
Thank you. So you briefly mentioned that the translational temperature of your ions in a trap is hotter than the buffer gas temperature due to arc heating. I was wondering, for the kind of reaction that you're looking at where they're dominated by tunneling effects, I would imagine like the hotter ions would play an outsized role in determining the reaction rate constant. So like even if you just have a little bit, you know, in your Boltzmann tail, right, it could distort your results. So how do you account for that effect?
That's also a very good question, because so in two answers. In this, we have not accounted for it, right? But in the tunneling measurement that I mentioned earlier, this was actually an extremely important effect, right? We actually saw much higher reaction rates, and we had to do very, expensive modeling to see, and it's not a Boltzmann tail, because it's actually a Thales distribution, which is actually, you have a higher population in the higher energies, and we did very careful modeling and could predict quite well actually what the extra reactions would be, and from that, with this combination, we could extract the low density or the rate that we would expect without this effect. And so in principle, I mean, we have the tools. In principle, we can do that here as well. That might be something to look into. Yeah.
And I guess a follow-up question is, what about the ions that are on the outskirts of your trap that are experiencing micromotion?
That is so. I mean, that's where the RF heating is, right? So these multipole traps, the way they, I mean, the reason we have multipole traps, right, is not just so that we have just kind of a more box-like potential, but because the inner part, is relatively, doesn't see micromotion, and you only see micromotion on the outside, right? And so the thermalization on the inner is heating free, and so that kind of wins over the heating on the outside. So you have you're right, a kind of a say smaller percentage that gets this heating, and that's where this whole extra distribution is coming from, this extra high Thales distribution.
I guess, heating, usually I think of as the energy in a micromotion being transferred into the secular motion.
Yeah.
Through collisions or other processes, right? But what about just the kinetic energy due to the micromotion?
I see. That ends up not being all that much, because what really happens, and this is also the same for for like a normal pole trap, a quadrupole trap, is that the energy of the secular motion is essentially transferred into this plus a little bit. I think maybe it's like a factor of 3 or so more total. So it's not huge energy amounts, but you're right. It is an effect, and one in principle needs to take that into account.
Thank you.
If you have motional states in an ion trap, then you would affect the motional states. You have quantized motional states.
Yeah, so I'm a little bit inspired by this the first reaction here. So, this is not a covalent bond, yeah? And I'm just wondering, you didn't measure that, but in how far is the hydrogen molecule kind of intact in the sense, for example, if I look at the rotational excitations, would the hydrogen rotational energy still exist in this chlorine compound? Or to what extent are they, the rotational motion of the hydrogen can be, although it's bound, still exist, and not the whole molecule rotates, just this hydrogen,
That's a good question. I don't think it's actively rotating, and I don't know. I think maybe you want to say something there. I'm not exactly sure. It is something that will be more interesting, or one of the reasons we want to go to para H2, right? Because then we can compare the normal H2 and the para H2, right? And so we have the different rotational states, and see what effect that has on this reaction. So it kind of goes in this direction. But more detailed answer of what this does, I'm not sure. I don't have.
I can maybe just quickly comment on this because we did, independently of this, we did experiments at Felix, at the free electron laser that Pavel already mentioned earlier.
Yeah, of course.
And we've seen the H2 versus chlorine minus vibrational frequencies both in the hindered rotation, that's what you mentioned, and in the stretching motion. So the H2 stretch itself was frozen, but this chlorine versus H2 stretch. And there are combination bands that we saw, not rotationally resolved, unfortunately, but we could do a very nice comparison with calculations that Thierry Stoffin and his team did. And they show that there is hindered rotation that actually leads to tunneling splittings, which is quite substantial. And also depends very significantly on the ortho-O'Hara, on the hyperfine state of the H2. And so it's this is actually a longer story. It's a very non-classical object. It looks simply non-covalently bonded, but it actually is quite a complicated quantum structure that you see depending on.
Interesting molecule, yeah.
It's really an interesting species.
A comment on this and then another comment about the argon, but I would think it might be relevant to this question you just raised, like what's the polarizability of H2 parallel and perpendicular? Do you know those numbers? Like these are quantities that often come into rotational wave packets. You need to know the parallel and perpendicular polarizabilities.
Yeah. I don't know them, no.
Calculations of that.
No, sorry.
Any of them known, yeah. I'm sure they're probably fairly similar in H2 because it's a pretty spherical electron cloud. Anyway, about the argon, I was just wondering whether you see argon 3+ as well.
It looks like we might see a little bit, but I'm not.
Not as
you know,
much as you saw
the-
with
yeah,
extra H2.
Yeah, we do. I mean,
In the first case.
this is preliminary, right? And put another level of preliminary on top of it. We do see some masses out here, really small ones, in the very high density regions, and we were considering what that is, and yeah, it could be that. Yeah.
Thanks.
More questions?
Yeah, I have a probably naive question about the exponents. So I saw several exponents, say t to the -1, and in the previous slides, I think Jesus and Chris computed the exponent to be like say 3/4. Usually in SETMAC, like those coefficients correspond to some universality or whatever. So may I ask if there's any universality or kind of other reasons behind those rational numbers or kind of magic numbers?
I think there are people in this room who would be absolutely much better at answering that question than I am. I don't know if someone.
Well,
This is-
the exponents we get are from the power law of the dominant long-range interaction, right? Jesus.
Yeah, that's my clue. Yeah.
So of course it's different if they were all neutrals than if there is a charge.
Yeah, it's based kind of on in two-body, you call a capture model. So we develop a capture model in 3D, sorry, for 3-body, and this is what we get.
Okay.
This is like also you have seen that for ion molecule reaction, things like that. These are these capture models, right? So we did the same.
Mostly dimensional scaling.
Yeah, that's right. It's only depending on the long range. So when you're very high on energy, all this is going to change. So our theory does not apply to the model.
Okay.
And maybe just to comment on that also, because it also depends on the internal structure a lot, right? I mean, so this t to the -3/4 is essentially for atom-like objects. When you do this with a large molecule, then the number of degrees of freedom that are coupling to the molecule actually add in. And that's what Robert was alluding to at the beginning, right? That there are old semi-classical statistical models where basically the number of degrees of freedom plus or minus, I don't know, half, something
degrees
like
of freedom plus 1 all divided by 2, that's all that.
goes in, right? And so many years ago we did a measurement on chlorine minus with methylchlorine free body recombination. So methylchlorine is a 5-atom system, and there the temperature dependence was T to the minus 3, and not T to the minus 1. So it's very, very different. In line with sort of counting the number of rotation degrees of freedom and adding also some of the intermolecular vibration degrees of freedom in, but it's all very hand wavy, and it's where we really need proper solid theory, I would say.
Right. Yeah. So just short question. What the inclusion of the Bose statistics? What does this essentially mean?
That's also a good question, and I'll go back to my disclaimer that this theory was, not developed by me, and so what this means, I mean, yeah.
Some kind of separation of thermal degrees of freedom. So I mean, it should somehow explain something, as far as I would expect. But
Yeah, I mean, as far as I know, is that what this shows is that this degree of freedom is maybe the dominant thing that explains this coupling, right? But beyond that, I don't want to go out on any more limb than that.